So next challenge for us here in this project. Well, so far we've written some code, we've tested some code, we've seen the outcome. Right here, the next challenge is how do we compute the size? And again, there is a proposed solution to this, is to say, how about if we create a function named size and say from this node, remember all of these member functions are invoked for a particular object, node A, node B, and so forth. So if we just say, okay, node A, B, and C, and then insert, and then if we say what is the size, then this function is invoked. And how about we define the size simply as a distance between this node, presumably, and this null pointer. Determine in what? In what units? In hops. How many hops does it take to here? And you can see 1, 2, 3 pretty much is consistent with the size of this list. One element, second element, and third element. So if we could only design a function which is smarter than size, which basically calculates the distance between node A and C, or A and null, and we can utilize this function in measuring the size. So here's the distance function, which in this particular situation does not is not recursive as the print was. This one is using a loop. So let's see what it does. It says measure distance to other nodes, and so it takes the other node, the pointer to another node. By the way, it not just takes the pointer to another node, but also says that other is a pointer to a constant node, intentionally restricting itself to only use functions which will not modify any data inside this node. Basically, distance should be immutable and should be safe, and so that's why this const comes in the in yet another type modifier in this pointer parameter. So other is a pointer to a constant node, intentionally restricting itself to pointing only to constant nodes. I will discuss these const qualifiers at the end of this lecture. Don't worry about this. Pretend that those weren't here. No this one or no that one. I'll explain them at the end of the lecture. All right. So now, we have the function that tries to measure this distance. So we say, how many hops will it take to get to this other node? So if this other node does exist, perhaps at least one hop will be required. So then we say, all right, let's pretend that we have some sort of an iterator. So let's make a little drawing of this. All right. So perhaps what we have in mind, that we have one little node, right? One node, and it has the next node pointer, right? And if I take this, Control C, and basically multiply it, this is where we're starting, and eventually the last one is pointing to null. Okay. So then when we start, right here, we say, let's start someplace. So I'm assuming we're starting here. So if this is node A, then we say a.size, right, in our code to compute the size. The size calls distance, and so this other is null, right? So other becomes null because distance is called from size member function with the null pointer. So other here is null. All right, then we say, so we try to create another pointer right here, and we call it an iterator, because we need to iterate inside our data structure. So, and we initialize it by saying, let's start with an iterator pointing to the next pointing to the next node. You see, because A does exist, the size was invoked for one of the nodes. That's why we kind of know that this node already exists. We don't have to count it or process it. What we start, we say, let's start with the next one right here. So we start with this one. Although the call came in on this node, we're already we're starting the processing part from the next node. And that's why we're already accounting for one hop and saying, okay, there's already this one and one hop already accomplished, simply by saying, let's start here. All right. Now we say, as long as this iterator is not equal to other, remember, other in our case is null. Then, as long as it doesn't equal, go inside the loop. And then we say, if this iterator happens to be pointing to null, then simply return. And return hops -1, because don't account for this last one. Like, it's just a simple -1 deduction here. Otherwise, advance the iterator. So say iterator should now equal iterator next. So what happens is that our iterator pointer assumes the value of this. So as a result of this line right here, we'll be moving on to here. And every time this line executes, iterator advances, right? And every time we say, as long as this iterator does not equal to other, in our case other is null, right? So we will detect this situation at the end of this iteration and say, oh, wait a minute, it's null. So it will return the counted hops -1, and hopefully this will be the correct answer. However, if we never if we run into the situation where someone invoked the distance function with non-null, to demonstrate, I could maybe I wanted to say right here we inserted everything right here. Remember, this was printing everything. So now I could say node A measure the distance to node C, for example, something like that. It's pretty universal function that it can count. It can tell us how far node C is located from node A on the list, right? So this doesn't have to be null all the time. This is just an example. Back to this slide. So basically, if other is not null, then at some point this iterator will reach. For instance, if I said A measure the distance to C, if this was B, right, and this was C, then at some point the iterator will be pointing to C, and iterator will equal other then, and so this loop will terminate. This condition no longer true. We get out and we simply return the number of hops. So this is this distance function, which also is a very typical demonstration of work that can be done on pointers. So anyway, if we add this to our little project, hopefully it all will work. So and then again, size becomes trivial, because size then says measure from here to the null, which is right at the very end of the entire list. Measure from here to null. and see 1, 2, 3. Oh, that's exactly the size of this list. 1, 2, and 3. 3 nodes are present. So by using this trickier version of measuring inside our list, we can accomplish size then by making this call. All right, so this one is kind of interesting one to have. And also it's important one because sometimes you want to measure the depth of your list, and that's this distance call. Print content of the list, another version of function which uses an iterator idea. However, what I did in my thinking here, I've used this recursive version of it, where I said, let's call it and let's keep calling it. The danger of this recursive call is that every time you making a function call, the stack frame, as you know, is constructed. Let me save this, make sure we save this.